So let's start the motion analysis. So motion analysis in case of spherical mirror. So far we have seen the point object which lies on the principal axis. But what if the point object is not on the uh, principal axis? If it is away from it. So if we have any object which is not on the principal axis, it is somewhere away. You can always do something like an arrow to represent the same, and it is same thing like the tip of the arrow is representing the object. Now, when we keep the object away from the principal axis, and of course, mind you that the distance is not uh, big enough to create the marginal rays. It is small enough. It is a few millimeters. If the the radius of curvature is in centimeter, this is just few millimeters. So in such scenario, the rays will remain paraxial even for the tip, because as I said that the tip is not far away from the axis compared to the size of the mirror. Now, when I say the size of the mirror, you can think as aperture also. You can think as a radius of curvature, or you can think as focal length. In paraxial approximation, everything is similar. So you can imagine the dimensional relation in that way. That is the object big enough to create margin rays? The answer is no. The mirror itself is very small. So technically, mirror is very small and object is also not very large. So any ray coming from the object till the pole will not subtend a big angle. So our approximation or the result that we obtain will be uh, perfectly okay and acceptable results, you can say. So now imagine this object starts moving this way. What will happen? The image will move parallel to the principal axis or will move somewhere else and somewhat different.
Parallel.
If this is the object, the image will never move parallel. That's interesting fact. Why? So we need to go back to the definition of magnification. So let's talk about the magnification again. So if you remember the magnification definition, which is pretty much straightforward, it's a size of the image upon size of the object. So we can say hi, which we don't know as of now. Uh, okay, upon ho. Okay, and this we can write as minus v by u if you remember. So we'll try to understand what the magnification means. It means like if the object distance is let's say ho, then what will be the image distance from the principal axis? And it turns out to be that it depends on the image position and object position with respect to pole of the mirror. And from the mirror formula, we know 1 plus u plus 1 plus 1 by u plus 1 plus v. So 1 by u plus 1 by v equals to 1 by f. And if I multiply with a u both sides, why I'm doing this? Because I want to express the answer only in terms of u and f, the object's position. The image position we want to avoid. Doing this will give you this opportunity of avoiding. So 1 minus u by f, if I bring this side and if I extend this side, this is minus u by f. So f minus u upon f is minus u by v. And therefore, the magnification which says minus v by u turns out to be, you can also write as f upon f minus u. And this is interesting. This is interesting because it is like minus f by x1. If you remember, the x1 was the object distance from the focal length, like focus. So if you subtract the u from f, what you get is the distance of object from the focus, and that's why this formula is very interesting because the magnification only depends on how far the object is from the focus. Instead of knowing the answer from the pole, this ratio can give you direct answer. And why it is interesting, because generally we know the f value, and uh, the x1 we can easily calculate mentally. And of course, if you know u, if you know f value of a mirror, you can just find the x, and then you can just substitute. So once you do it, I mean, of course, it won't be a very difficult job for you to consider. And of course, x1, how we define x1? U minus f. That's why I wrote the formula minus f by x1. So this is the way. This is how we are going to define it. Okay. You can of course put the sign convention and whatever you want, and you can get the answer. So once you know that magnification depends on the object position, okay, or f minus u, this will also give you the idea. X1 is the distance from the focus. So when x1 will be 0, when u and f will coincide, right? So when the object is at focus, m becomes how much? Infinity. Can you see that? The formula directly claim give you the claim. Yeah, if x1 is 0, the m becomes infinite. Correct? So when the
Yes.
object will tends towards the focus, the image will tends towards infinity. Okay, I mean it will be infinitely magnified, which means the image will be infinitely away from the principal axis. Correct. So now this x1 is interesting because it gives us the less number of variable to deal with. Like if we express the answer in terms of distance from the focus instead of doing it from pole, then the formula becomes pretty easy. Understood? And if you try to apply this method or this formula to find the magnification, you can do it mostly mentally. So let me give you one simple example. Maybe in high school you have been doing questions like this, but let's see how easy is this to solve now, just with this formula. Like, no need to do anything. So let's say if I tell you that the focal length of a mirror is 10 centimeter and the object is kept, let's say at 15 centimeter. I mean, that's so simple. And the object is somewhere here. Let's say the object is here. And the height of the object is, let's say, 2 millimeter. The focal length is somewhere here, right? The 10 value. So how far is the object from the focal length? You can clearly see this is 5. So magnification will be how much? Minus, and f we write as minus 10 because for concave mirror the f is minus 10. We have to substitute with sign, and the x1 will be how much? So the distance is 5, and we can add minus 5. Why minus 5? Because the x1 is behind and then left. So the value turns out to be how much? Minus of minus 10 upon or minus 5, or if you want, you can add in detail like minus of minus 10, not minus 10. If you want to use the direct formula, the formula which we had, like f upon f minus u. So f will be minus 10. Minus 10 minus minus 15. What I'm getting? minus 10, f is minus 10, and u is minus 15. So this turns out to be how much? Minus 10 by value which is minus plus 5. So m turns out to be 2. And if you use the direct formula minus f by x1 minus of minus 10, if I'm using this formula minus f by x1. And how we define x1? So u minus f. So minus 15 and minus of minus 10. That's how we define x1. And that's why the x1 turns out to be the value wise minus of minus 10. And x1 by definition is u minus f, which is like finding the distance and taking the sign. And how to take the sign is again simple, I think. If u is less than f, it will become automatically positive. So in a way, you can say if it is on the right side, it's positive, left side, it's negative. But if this gives you the confusion while writing this answer, you can just use this formula. That's pretty much straightforward. So I'm writing here is minus 5 because I can see the gap, and the gap is this much. Okay. So minus 2, same as. At least to know the magnification. See, I mean, even when I am solving the question, I don't do all these things because I know that the distance is 5 and the f is 10, so I will get right 2. And because I know it's beyond f, so image must be real, so minus. This is how I solve. As a beginner, if you don't realize that every real image must have the negative magnification, every virtual must have the positive magnification. In that way, you have to write everything. But once you realize that how to solve, just find the numerical answer, put plus minus as per your knowledge. If you know it's real, make it minus. If it is virtual, make it plus. So that's pretty easy if you are just solving problem. Okay, this is how I think. Now getting the magnification minus 2, which means the height of the image upon height of the object will be this answer, minus 2. That's it. Which means the height of image is how much? And negative is saying that it will be inverted. So of course, once you are between, let's say, C and F, if the object is between C and F, the image will be beyond C. I mean, of course, I cannot show it because space is the constant. But you can realize this. Now, what you need to realize that a moving object, if an object is in continuous motion, the x1 is a variable quantity. X1 will keep on varying. Do you realize this? Or you can say the
Yes,
u
sir.
is always varying. So the height will be also always varying. Okay. So what I'm trying to say that object here is beyond C, and we know that for a given position the image will be somewhere here, maybe somewhere here. From the knowledge of image formation, we know something like this. But as it will move forward, the size, so the object will go left, but the size will also increase, right? Because at C they must have same size. I hope you realize this fact. So coming to C, the size will become equal, correct? And the moment the object will cross the C position, the image start becoming even bigger. What I'm trying to convey that the object is not trying to move this way; it's trying to move this way. Can you see the tip?
Yes, sir.
And the tip is giving you a hint that the object never moves a straight line. Sorry, the image. The object, although moving a straight line, the image will shift left and away from the principal axis because of magnification. Yeah, I think your idea of motion is because of the foot of the object. This point. Yeah, this point is always moving left, but the tip, if you think, the tip is the image. The tip will keep on moving in this fashion. And the moment you reach the F, the tip will become infinitely away. I mean, I cannot show it actually. That's very interesting. So when we try to analyze the motion of the object and its image, we have to explain the two types of motion. So I can say that every image will have two motion. One called the transverse motion, let's call it Vy, and the longitudinal motion, let's call it Vx. So image will have two component of velocity, x and y, whereas the object is only having the x component in this particular situation. Let's call it the u naught is the velocity of the object. So only when the object lies on the principal axis, then only the magnification part will never work, because m needs some h naught to magnify. If h naught is 0, I mean you cannot magnify anything. Understood? So it will never go away from the principal axis. Okay, it will remain on the principal axis no matter what. Okay. And if 0 is magnified infinite times, it remains 0, because 0 into any number is 0. So even the magnification is infinity, it really doesn't matter. Understood?
Yes, sir.
So the magnification will only work if the object is away from the principal axis. If it is on the principal axis, no matter where you are, no matter what's your position, and no matter what's your magnification, you will remain on the principal axis. So magnification cannot take it away. I mean, only if you are already away from the axis, then the magnification will have a role to play. Otherwise, it will never play any role in solving the matter. So this is pretty much easy. Like you can do variety of question by this relation. So let me show you some interesting question of SC Verma, which we can do almost mentally. And it looks like difficult question maybe, but it's almost doable mentally. And I'll show you how. So, okay, I need to have this book. Anyway, I have shared the resonance sheet of
Yes, sir.
optics. Please open it. Open it. Yeah. Oh, I shared it yesterday on the last lecture. And okay, maybe okay. And go to the advanced level problem. The first question, you can do it mentally almost. Advanced level problem. It's page number 53 actually. So page number 53, because this is from SC1 and there is an object, and see how we can solve like almost in one line without doing any calculation much, because we know some of the better methods of solving the optics problem. So when numbers are given, you can do the calculation much faster. This is 2 centimeter. This is 5 centimeter, and this is 15 centimeter. Okay, and the radius of curvature is given 20 centimeter, which means the focal length is how much for paraxial approximation, if you remember, r by 2. So 10 centimeter, and the question is find the total length of image. Like how much AB will become, how much BC will become, and how much CD will become. Okay, and everything is given to you. So of course the focal length will be somewhere here. The focus will be here, like 10 centimeter away. Then you can see the B is how much away? How far?
5.
5. Okay. So for B, we know 5. So the XB is 5. So what will be the image of XB? Let's call XB dash image position of b. So we can use the which formula? Newton's formula. Xb into xb dash equals to f square. That's pretty easy, no? So 100 upon 5, which is 20. So b will be available at 20 centimeter from the focus. Now remember, its answer is from focus, not from the pole. Correct?
Yes.
20 from focus means 30 from pole. Correct?
Yes, sir. 30 from pole.
Yeah. So these are from focus. Okay. Let's see. Pretty easy. So we got the answer of B location. Similarly for C. Again, use the Newton's formula. How much far from the focal length? 5 plus 5, 10.
10.
So this will become 10 centimeters. So the C will flip on the right side, right? So 10 from the where? Oh, so it must be. Oh, sorry. This is at center of curvature. No? So it is at C only. 10 from F means 20 only. So it will be there only. So C will not shift, isn't it? Because okay, you can see directly the C itself is the center of curvature. Do you realize this? 20 centimeter is ROC, the radius of curvature, and the C is
Yes,
at
sir.
20 from the pole. So C will never shift. So C will be there. B will go on the left side, 20, which is 30 from the. So 10 on the left side. So now the shape will be like this. B will be shifting this side, and the distance becomes. I hope you can see this. B dash C dash will have the separation of 10. Do you realize this fact? The B is 30 from the pole, C is 20 from the pole. So where is B dash?
Yes.
10 away.
Yes.
So I got the stretch of the BC part of the object, because this is on the axis. So we have to find the actual position, and then we can find the size of the image. So we got the size of the image. Okay. And we can clearly see it has flipped. It means it is a like a negative magnification, because the if I have some arrow here, the image will have arrow like this. So it's like flipping. B is on the left and C is on the right. Anyway, so we got the BC part. Let's talk about the AB and CD part, because that's pretty easy. You can do it almost mentally. So what is the magnification for the AB part? Magnification for AB part. M will be how much? Just write the value directly. F upon distance from the focus. And distance from the focus is how much? 5. And we can put minus n because of course we know it's real. Minus 2, which means the size of the AB part will become how much times?
2
2.
times, but inverted.
So the AB part will be like something like bigger. It's 4 centimeter now. Done. Very easy. And look at the CD part. For CD, what is the magnification? You can do it directly. F upon, and distance from the F is how much? The C, 10, and nothing. Why nothing? Because if the object is at C, it will never magnify. It will remain of same size. We know this anyway answer, but anyway, you can do it like this, and this will become of same size too. So what is the total length now? 2 plus 10 plus 4. So total length of image is equals to 4 plus 10 plus 2, which is 16 centimeter. Am I correct? Yeah, maybe. I think you can check the answer. Oh,
Sir, it's
6.
16 is correct.
So you can see that these questions we can do mentally without writing the UV relation, without writing mirror formula. So what we are applying is the latest one, the Newton's formula. And of course, the magnification is pretty easy to write if you write in terms of f by x1. And always I will tell you that if you want to know the value, just use f by x1 and decide the sign on your own with your common sense. Okay, the sign should be positive or negative. Yeah, of course, it is anything beyond f, the concave will form the real image, right? If you know this little fact, you can get it. So this approach is very much effective and powerful. And of course, sometimes when we get confused, we use the when the numbers are not there, when we don't have the symbol. I mean, sorry, values of distance or position. There we go back to the very fundamental one by u plus 1 by v equals to minus, because we don't know the value, so we cannot decide whether it's left or right or something like that. Okay. Then you can go to the question. Okay. So I'll tell you the next question. So we'll come to the motion analysis again. Uh, but let's do some problem because we are doing it. No problem. Yeah. So come to the page number 11. Can you see the page number 11?
Sir, which one?
Your sheet, resonance sheet.
Sir, yes, question number.
Question number B3. Again, you can see B3. A very much similar question. Can you see it?
Okay, I'll tell the page number.
Page number 11 of the PDF. It's 12 of
Sir, got it.
what is no, B3. Can you see B3?
Yes,
Square ABCD of 1 millimeter.
yes, yes.
Yeah, no, this is very much a realistic question because 1 mm is something for which we can apply the approximation without much difficulty. So try to solve B3 and B1 and B2. Okay, solve B1, B2, B3, all three. That's pretty easy. Try to apply the methods and see how comfortable you are. Okay, so go ahead and solve B1, B2, B3. And try using the Newton's formula and the magnification in terms of distance from the focus instead of doing from the pole all the time.
So first one is A. No.
Hello guys, you solved the question? B1, B2, B3?
Yes, sir. So first one is A.
First one you
Second
got
one.
the answer?
Yes.
Excellent. So solve the second and third. First, second, third we just saw how to attempt. So anyway, I hope you can do it. Finish it. Okay, all three done?
So second one done, sir. Can you solve the third one?
No, why I should solve? In the third one,
So that
once you know,
length BC will remain same.
see, once you solve it, you can see it will become trapezium, right? Isn't it? And it's a not trapezium because it's a very small in size, so you can almost take as a rectangle. Maybe the base will have different length and the height will be different. So okay, I'll solve the third one. I think I got it. What's the problem? The third one is interesting. The very small size will take you to the concept of something called longitudinal magnification, if you remember. I hope you remember. Do you remember longitudinal magnification?
So can you
Because
repeat?
yeah, because the base is very small. No? How much? Just how much? Few centimeters. Um, come on, where is the base length given? 1 millimeter. Yeah. So I cannot write the mirror formula with 1 meter, 1 millimeter difference with a 2 centimeter because that's very small, right? So the trick that will work here is longitudinal magnification formula. If you remember, I hope you remember. Do you remember?
Yes.
No. Longitudinal magnification is square of the linear magnification if it is really small. So for a small object, what I have written, for a small object, what we write? dv by du, which turns out to be minus m square. Do you realize this? M longitudinal. Sorry. And m is the linear square, linear magnification square. So you can write as f by x1 whole square. Let's say x1 is the, or let's say x1. So xo is the distance from the focus. Okay. And the object as given in the problem. So because this is 1 millimeter, so we can just think this is a 1 point object at a distance of 15 centimeter, correct?
Yes.
And the focal length is how much given? Uh, 10. Read the question and tell me the answer, guys. Come on. So given this is 10 and given this is 15, the f is somewhere here. Again, what is the x naught now? You can see what is x naught?
5.
Just
No.
write the value.
10.
Yeah, 5. Why 10? 5, na? 10 is this. Come on.
Sorry, 5.
X naught is always the distance from the focus, no? So we are done. So what is the longitudinal magnification? Minus 10 by 5. Sign doesn't matter. Minus 4. Which means the entire body will stretch by 4 times. So if it is 1 mm, it will become 4 mm now below. And this we can keep it how much? So this is 1 mm. Oh, sorry, I made a mistake here. This will become 4. The longitudinal magnification is how much? 4 times? My bad. So I can show you the exact diagram. The C will be here, and just a moment. So the object will stretch like something like this. How many times? 4 mm. This is how much? 4 mm. And what about the magnification part? Linear magnification is only 2, you can see. The linear was 2, right? F by x naught, and therefore this will come 2 times. So 4, 2, 4. What is the total length roughly?
12.
12. Is there an answer 12 like this? Do we have
Yes, sir.
answer 12?
12.
The total length. So what we applied here? The concept of tiny object. And in case of tiny object, if the two ends of the objects are not far away, it means if the difference is in millimeter, whereas the focal length is in centimeter, or if the radius of curvature is in centimeter, you can use the longitudinal magnification by this relation. I hope you remember. Once again, let me derive once again. If you differentiate, you can have dv by v square plus minus du by u square equals to 0. Okay. So minus dv by du turns out to be how much? I mean, sorry, dv by du is minus v square by u square. And this is simply the linear magnification whole square. So that's why this is minus m square. And this we can write as f by xo whole square. I mean, of course, you can write like this. So when objects du is very small, when this is very small, so this is like 1 mm. So dv is how much? Minus m. Just Just okay. So now dv will be how much? It's of course minus m square into dv. So this is how you can use, and that's why the stretch of the 2 points at the on the principal axis will be the m square times the stretch of the object. So the image separation is m square times object separation on the principal axis. This is called the longitudinal separation. Longitudinal separation of object, and this is the longitudinal separation of image. So these are simple things which you can apply and remember. I hope this is clear, guys.
Yes.
Yes.
All right. So let's do the next problem. So we will do some interesting problem. Like if we have a mirror, just give me. Okay. So let's say we have a concave mirror of focal length f, and f is the value, not symbol. Focal length itself is f. Okay. This is your principal axis. A parallel beam of light is coming from infinity. Okay. A parallel beam is coming. Okay. No, this is how to do this. So parallel beam of light is coming. And now what we do is we have a coin. So we put a coin here. The radius of the coin is unknown. Okay. And the coin is kept at a distance of the coin is kept at a distance of let's call it f by 3. Yeah, that's fine. And the beam is also circular. Of course, beam is circular. And the beam radius is how much? Beam radius is capital R. So find the minimum radius of a coin to block all the rays from reaching the principal axis. What is the question? Question is anyway interesting. Simple geometry, basic class 10. Find the minimum radius of disk to completely block the rays from reaching the disk, reaching the principal axis. I hope question is clear, guys.
Yes.
Okay. So that coin is definitely kept symmetrical. So no ambiguity about the how it is positioned. That's symmetrically kept, and it is normal to the principal axis also. And this is the parallel beam of light. Okay, what is this? Parallel beam of light. Okay, I can change the color. Change the size. Okay. Questions clear, guys?
Yes, sir.
So try solving it.
Sir, what?
Are you solving it? No, you're supposed to solve this. I mean, question is find the minimum radius of the disk to block the rays from reaching the principal axis. The coin is kept at a distance of a by 3 from the pole. Okay.
Yes.
So you want to attempt this or shall I solve this right now?
So attempt.
Great. Please go ahead. Any parallel beam after reflection will try to meet where? At focus, correct? So let's say this
Yes.
beam after converging is trying to meet here. Let's say. Then the disk must be of what side? So we must make sure that the disk is up to here, correct?
Yes.
Then only it can block everything. And if it is meeting here, so this must be equals to F. So we are only supposed to find the similar triangle, and it's done. So capital R upon F, capital R upon full length is must equals to small r upon 2f by 3, because that distance is 2f by 3. A by 3 is from the pole, so from the other side it's 2a by 3. And the answer is at least 2/3 of the radius. Anything bigger will anyway block, so the minimum required to block is 2/3 of radius. I hope this is clear.
Oh, yes, sir.
Understood. The idea was any light ray coming after reflection must be blocked by the this point. Something like this you can think. So what you are supposed to use? A simple concept of similar triangle. Okay. So let's do something more about this. And this is just a beginning. Uh,
So, so this lecture is till what time?
Pardon?
This lecture is till what time?
4 o'clock.
Okay, sir.
It's a short lecture because I missed
So
the
now
morning,
because I have to go to the lecture for math.
but that is from 6 o'clock, no?
Sir, yes, I have to do the preparation as well, that I have to do solving. So
No problem. Anyway, 20 minutes I will leave. So that's why I have kept only for the problem solving. I'm not going to teach something in here. So now let's say we have a concave mirror of focal length that's called 10 centimeter. And what we do is we have a plane mirror which is kept somewhere here, only half of it. Okay. So we have, and the distance between them, because there's nothing mentioned, you can say this the distance is 50 centimeter. Okay. So an object is kept in between the mirror with unknown value. I mean, like I don't know where it is. So let's call it D. So find the D value such that the first image formed by the plane mirror and the first image formed by the concave mirror both coincides. Questions clear?
yes.
So we are supposed to find D such that the image of plane mirror and spherical mirror, or you can say concave mirror, I must get the first image. Both coincides. Okay. So that's a simple, straightforward question. So try solving this and you will get the answer. So you are supposed to find the D value such that both images coincides. think for a while, then I will stop. So I'll keep this as the last question, then we can leave for the day.
Sir, on radius of curvature, number means 30 centimeter.
Pardon? Tell me.
So 30 centimeter. D.
Okay, T is coming 30 centimeter. Okay. Okay, so the first image by the mirror will be somewhere here, right? D away.
Yes.
and this should act as the image for the concave mirror as well. So for concave mirror, f is 10, the rest is 40. So what is the distance of image from the focal length?
D plus 40.
Yeah, so it's a d plus 40. And what is the distance of object from the focal length?
40 minus D.
And this must be equal to
100.
it's just a quadratic. I think this is minus d square minus 40 square, right? A plus b into a minus b. Okay. And this is equals to 100. So d square minus 1600 is how much? Minus 100. So d square turns out to be 1500, right? So d is under root of, or you can say 10 root 15, right? Roughly this turns out to be 40, right? Slightly less than 40. Oh my god. It should be somewhere there. Alright, so this is the answer. Or you can solve by the UV formula 1 by U plus 1 by V 1 by F. So what is U here? The U will be 50 minus D, right? That's easy. And what is V here? 50 plus D with minus. And what is F? Minus 10. So again, this will cancel out. So this will be 1 by 50 minus D. You can take the LCM, whatever you want to do. Solve it. Let me just match it. I mean, there should not be any problem. So 100 upon 50 square minus D square is 1 by 10. So 50 square is how much? 2500 minus D square equals to 1000. So D square is how much?
15.
So you can see the answer is 10 root 50. Okay. So you can see that whatever method you may apply, whether you use the Newton's formula or use the classic UV formula, the mirror formula, the answer turns out to be same. Okay, so you can choose whatever method you're comfortable with, and I will suggest that try to use Newton's formula as much as possible. Generally, it increases the speed of solving. Okay. All right, so no problem. You can go for your math lecture. I'll continue the same in the next lecture. Bye and take care.